aspect ratio is infinite, this equation becomes this one. And you can actually see that as you begin to look at these data sets. It becomes pretty obvious that this is a subset of that. That's a home run. And then the literature suggests, excuse me, I've been shouting too much. The literature suggests that in the extreme, when these systems become such that they have an infinite aspect ratio, it suggests that they do not go into pseudosteady state. Oh, come on. That would say, theoretically, in theory and practice, if a linear flow system cannot go into pseudosteady state, then one well is all it takes to drain the entire universe. How stupid is that? Well, that's not true. Because it doesn't matter the flow geometry, the well will ultimately go into pseudosteady state. Now, I need to put on the table before you a caveat to that. Burry and Cox published a paper, it's I think about 1996, paper time frame. Burry and Cox published a paper because Marathon was having just a devil of a time looking at the performance of these wells. They saw that as the well would age, it appeared to go into pseudosteady state. Very commonly would go into pseudosteady state, what looked like pseudosteady state. And they realized that based on the geologic evidence, that didn't make any sense. Because it was as if the well was producing from 1, 2, 3, 5 acres, when they knew geologically it had to be producing from 10, 20, 50, 100 acres. And yet they were seeing, based on the production performance, that it looked as if it was producing from a very small drained area. So what they published was a discussion about the fact that skin is not constant. We have the concept of time-dependent skin. And time-dependent skin, that is to say S, and we've already talked about psi d being a function of time, and there's a function of time. What they showed, very compellingly, is that skin is a function of time, and invariably it increases. The well's condition, the degree of damage, worsens as it ages. And it looks like the signature of that, the signature of time-dependent skin, is that the well looks as if it has gone into pseudosteady state. Whoa, that's kind of an important idea. So, onset to middle time. Back to my picture with you about throwing rocks into the puddle. When I throw a rock in the puddle, if the rock lands in the middle of the puddle, and my puddle is circular, that wave will hit all sides simultaneously, won't it? Suppose now my puddle is square. Throw a rock out into the middle of it, it hits 4 points simultaneously, and then after a while it finally reaches the corners. Well, that's the work Matthews, Bruns, and Hazebrook of New Texas did. This was an awesome piece of work. This was all done with an analytic simulator, not a digital computer at all. It was the old analytic models that we used to use back at the turn of the century, literally. This work was done with that, and what they were looking at was the transition from infinite acting over here as you come onto the graph, and how the signature would change for various geometries as it went into pseudosteady state. You see that. Unfortunately, usually at this point in the life of the well, there's so much other stuff going on that I've concluded that this is largely unusable data. Not because it's not there, it's just that we don't have a means of making it useful. But clearly, the way the pressure wave hits the boundaries and how the boundaries move. You say, well, yeah, unfortunately they do. Suppose I looked at a well, and maybe it has not yet gone into pseudosteady state. I'm going to look at it today. I'm going to look at the pressure contacted volume. All right, the pressure wave has moved out so far. But it's not in pseudosteady state. It's still infinite acting. Tomorrow, when I look at this same well, what am I going to see as a drained area? Today it looks this big. Still infinite acting. What am I going to see tomorrow? Huh? Why? Why?
You have more time for that wave to go towards the boundaries?
Now say it like you mean it.
It would be larger.
Why?
Because it takes longer for that pressure wave to reach the boundary. Are you sure?
Well, you're right. I mean, you're absolutely right. But I'm not joking. Now tell us why convincingly. Because you are right. You are correct.
It hasn't reached the boundary yet.
It hasn't reached the boundary, so that pressure wave is doing what? Still moving. It's expanding in volume. So the bad news is, just because I know it drained this much area today, I know that tomorrow it will. Precisely. Well, let's be careful. Let me argue with you about your choice of words, because your idea is right. Is it going to be necessarily a larger area? Right on. Right on. And that's really a crucial idea, because the pressure wave is not just going to move horizontally, it can also move vertically. And so it's going to be a larger volume. You're right on. See that? See why? Can you think about how that... I mean, basically what we're thinking about, the mental picture I have of this is a balloon. Just a classic blow it up kind of balloon, a rubber balloon. But the rubber in the balloon is not uniform thickness. Over here it's really thick, over here it's really thin, what have you. So when you blow it up, some of it's going to stretch a lot, and others of it, because the rubber is much thicker, is not going to stretch so much. All right? So it grows, because I'm going to continue to blow into it. The balloon is growing all the time until it bursts. Don't get into that analogy about pseudostatics. But the picture is the pressure wave, this volume of rock that is contacted by the pressure wave, does not change symmetrically, does not change horizontally. It's moving in every possible direction, and probably because of this anisotropy concept, not uniformly in any given direction. All right? Does that make some sense? Our mental picture, I say this with absolute sincerity because I am guilty. I taught reservoir engineering to engineers who believed in pie pans. My reservoir is circular, uniform thickness, head. I now believe that reservoirs look like this amorphous balloon. All kinds of weird shapes, lumps, bubbles, what have you on it. And that really has changed my view of the physics of the system. And that's why Matthews, Browns, and Hazelbrook work really is important to us. But by this stage in the life of the well, typically the data is so bad that we can't use it quantitatively. All right? But it's important. All right, so, he's about to quit. Yay! Party time. No, not quite. Well, the RPI method allows for the interpretation of production data with varying rates and pressures to estimate initial pressure, effective permeability or conductivity, apparent fracture length, and drain volume. All right? So there's some corrections you need to make to your notes because my conclusion is incorrect. Now, you say, well, geez, Crafton, you put a slide out there with stuff on it that's wrong. One of the things I firmly believe about the teaching method is it's okay to tell you stuff that's wrong as long as it becomes useful when you look at it and say, oh, it isn't about the effective permeability, it's about the effective conductivity, and more precisely, it's about the effective transmissibility. What was the definition of transmissibility? H over mu, right? Good. There you go. What about drained area? I just beat up on him unmercifully, and he got it right. It's about volume, pressure contacted volume, because I really don't know where it is, and I know for sure, I know absolutely for sure, it's not a pie pan. Okay?
Because you said we can't really solve for them because we don't have the tools available to us. Are they tangible heights, or is it like a column, a continuous height column? And my other question was, we're talking about things that are flat right now, and I know that we're not talking about the geology, but I am aware of unconformities and stuff that can bring gravity into effect just by having an incline.
Yep. Question is, first piece is what about the thicknesses? How do they work? And the second question is, when you get into these multidimensional systems, how does gravity play into that discussion? And let me kind of work the problem backwards. The gravity issue is why I make such a big deal about where you measure stuff, and then you try to transform everything to a consistent datum.
Okay.
Because in classic hydrology, for example, if you had a fluid mech class yet, in fluid mech they talk about the hydraulic grade line. The hydraulic grade line essentially tries to remove the question of elevation from the discussion, rho GH. And that's basically what they're doing there, is they're saying, okay, I know how my rho GH changes in space or in time, and I want to bring it back to the grade line, which really in our terminology would just simply be like mid-pay. Okay, so we're going to take it to a specific datum. So it's basically that idea. So what I'm really engaging here is the idea that if I take everything to that common datum, then essentially I have taken that out of the discussion. Now, truth of the matter is I probably haven't, because I don't really understand what that geometry might be 100 feet away. But at least as best effect I can, I have removed that piece from the discussion. That takes us back to the discussion about thicknesses and how they work. Because, and I told you the story about Terra del Fuego and the shallow Niobrara and what have you, my gas storage system. I dare say that I have, now that I know now that I've developed this set of prejudices about the way thicknesses behave, I don't think I have seen a single well in which I believe the phi 1 minus SWH numbers that we use. Now, that's not to say they're not useful, okay? I didn't say that. I mean, it's worthwhile to have the log analyst do the calculation, because at least it gives us a framework in which to do business. But the bad news is, Mother Nature's flow system, the log analyst didn't call up and say, hey, there's that disconnect between what the physics of the real world are and what our hypothesis about the real world is. So I think that's the dichotomy. That's the problem we run into, is we've got this disconnect between the reality and the model we use. That implies, in my book, that we cannot know what that thickness is, or those thicknesses are. Okay? They're basically unknowable. But I still have the ability, because the thing that's important is on the Horner plot, or on these MDH plots that we're going to talk about, or on the supersteady state plot, the slope of the line includes the thickness. It's embedded in the calculation. So it's a sad statement about things. I'm going to count you. Craftsman, I got this core report, and the core report says that the permeability is 3.725 millidarcies. Okay, that's really cool. I'm just so proud of you that you have that. Done enough core work. Got this really nice core laying out here, laid out. Boy, it's pretty, it's neat. Wow, look at that. Oh, yeah, ooh, ah, all the stuff. And oh, by the way, take me a core sample right here. Well, if right here happens to be a place where there was no core, because we couldn't retrieve it right there, how do I get a core sample? Right? I mean, you probably guys haven't yet had a whole lot of work with core data, but it's very common that you'll have a chunk of core, very competent, and then there'll be a piece missing. A foot, 2 feet, 2 inches, whatever, and then here'll be another chunk and what have you. The only place I can take core data is where the rock is mechanically competent. In statistics, that is referred to as a biased sample. I have just biased the sample because I cannot take samples where I don't have samples to take. What's that? Wait. The competent rock is most likely also that rock which is likely to have the lowest permeability, simply because it is mechanically competent. Oh crap. Pardon me. Oh shucks. Sounds nicer, doesn't it? So I am deliberately taking core plugs from pieces of rock that are sufficiently mechanically competent that I can drill them out, process them, and run the permeability experiment. So I have just automatically biased my calculation of permeability to values which are persistently low. Piece of bad news. When you look at these resource plays and you use the thicknesses that are reported, you will wind up with permeabilities that are literally hundreds to thousands of times higher than the core forms that are measured. What's wrong? Who screwed up? Well, I took the core plug from my sample that I was able to retrieve that was mechanically competent, and it calculated 5 nanodarcies. Then I went over here and I did this production analysis nonsense, and if I use the same thickness that the petrophysicist gave me, I calculate 2 millidarcies. One of those two numbers is wrong. Which one and why? Which one and why? Because obviously that core plug is a piece of real rock sampled and measured competently by people who know what they're doing. Yeah? 5 nanodarcies. And I looked at the production history and it showed me a radically different picture. Which was wrong. One of them has to be wrong. Yet, I did my production analysis with theory that Crafton says is valid. The rates are valid because I know I received a check for them. So that's good. What's wrong with that calculation? Which piece of the process failed?
Both would be a little bit wrong with that.
Well, I'm willing to stipulate to you that the perms that I measured with the core are correct for that chunk of rock.
But not for yourself.
That's the point. Now you're onto it. Now you're on it. That zone, I mean, here's chunks of rock that I couldn't recover. They were probably not mechanically competent. And very likely, because they were not mechanically competent, they actually had much higher permeabilities. It would seem logical to me that that would be the scenario, because maybe they were in a fractured zone, maybe they were in different mineralization, what have you. When I look at a production history, I'm looking at untold zone. I don't know whether it's the zone I calculated the porosity crossover or not, but it's a zone that is unconstrained. Whatever can produce at that pressure will. So I'm seeing all of the rock interval. When I do the core plug, I'm looking at a sample that is biased to the low end. So anything I measure as a permeability in it is going to be persistently lower than what is really available to me. I think that really did it. Now, but we still haven't resolved the question. Because here's this perm core, this core perm. I have no reason to think it's terribly wrong. They did the Klinkenberg correction for it. They did the stress correction for it. They cooked it right. All the stuff was done correctly. I mean, it was a competent piece of work. And it got 5 nanodarcies. And now I look at the production history and I get 2 millidarcies. I'm still back to the debate, which was wrong. Well, neither one of the processes were wrong. It's the fact that I didn't use a correct thickness. The thickness from which I calculated that 2 millidarcies was the thickness that had porosity crossover. Remember my discussion about the Niobrara. The porosity crossover was literally about 1/10 of the total thickness that was exhibited by the Niobrara. Well, there's a tenfold change in what I would calculate as a perm right there. And I can tell you with absolute confidence, I have looked at systems like the 14,000 footer in McMullen County, Texas. They were using 20 feet, and I know for sure that that well was actually producing from at least 5,000 feet. You think the perm's going to be wrong on that one? Yeah, huge difference. Well, it really does go back to the debate. Do I need to know that thickness? Well, yes, I do, because what I've just told you, and my client that had this event happen to him, is now drilling wells for the purpose of completing these other zones. Wow, that's cool, because that's going to add a huge amount of value. Let me give you an anecdote from the other side of the coin. One of my former clients leased only the Eagleford. The Eagleford's a relatively definable geologic interval. They leased only the Eagleford. They started producing the wells and discovered that they were having pressure support from a far greater thickness than just the Eagleford. They were producing hydrocarbons from rock that they did not own the rights to. Stop and think about what I just told you. They put themselves in an untenable legal situation because they were violating the correlative rights of those intervals that belonged to somebody else. See that? They finally realized that they were committing a very serious crime, actually. That was theft. I mean, that was prima facie theft. And because they were thieving from the people that owned, the companies that owned the other two zones above and below, that theft was actionable. And rather than try to fight that in court, they abandoned the wells and sold the leases.
Why would they have been leased that in the first place?
Well, that's another question. Well, but it goes back to our discussion about thickness, because they were of this frame of mind. I know the thickness, it's just the Eagle Ford. The Eagle Ford is the only thing that produces. And then when we started looking at the production histories, it was obvious that considerably more volume was contributing. So they were stuck in their traditional mentality. By gosh, porosity thickness is the thickness that production comes from. And then they looked at this issue of storage thickness, and it was obvious to them that pore volume was different. I mean, I got to tell you, you say, well, gee, that kind of back to his thesis about what's conventional wisdom versus my heresy. Conventional wisdom, they did right. That decision to lease the Eagle Ford and do nothing else, that was a valid decision in traditional view of the world. But then when they started looking at the well's performance, their traditional view of the world was discovered to be erroneous. And it had very compelling legal consequences. Stop thinking about that. I mean, here's corroborative rights being violated massively. How do you go to this other party and say, well, by the way, Fred, I just stole the half a BCF from you. And Fred's going to say, like the heck you did, that was a full BCF. Or whatever units you want to use. But the point is, just like knowing the thickness, it was impossible to know the volume of hydrocarbons that were borrowed from the offset zones. They had an absolutely untenable situation. They couldn't handle it. And they made a wise decision. It cost them pushing $100 million of liability to abandon the lease. And it was a big deal. But they did, and I think in my mind it was a wise decision to take that hit rather than the possibility of having to go to court and suffer the consequences of the legal battle, because they'd have lost that out big time.
It kind of brought up another question I had about the production data. I worked on a project where I was looking at production data in Colorado, and I was, like you say, a lot of operators, if they're not selling the gas, don't report it.
Yeah.
And like in Farmington, with the water production, it sits in open pit.
Yep.
If the tank ever fills up, which normally it doesn't, then they'll report it when it gets hauled.
They'll report tank hauls, but nothing else.
Right. So how reliable is the public information that we can get? And then how much data, and then I guess another question would be, how much data do you need? Do you need 2 years, 3 years, 4 years, versus a shut-in test where, I mean, in the maximum 96 hours, and you can come up.
Well, let's deal with it this way, because you've asked me two different questions.
Right.
The issue about duration of a test, which is basically the 96 or 72 or whatever length of time the shut-in lasts for, versus a production history which could last for years. When you think about this idea of dimensionless time, presuming that both experiments, the production test and the shut-in test, are on the same reservoir, and for discussion purposes, let's concede that the reservoir stayed the same. Okay, fracture length there, none of the things which could have varied did. All that changed was time, and pressures. Okay, that's all, nothing else. The physical condition did not change. Which one of those experiments saw more volume of the reservoir?
The production, obviously.
Exactly. Did the production test see the same reservoir as the buildup? Knowing that the production test saw more reservoir volume, let me ask it a different way. Did the buildup test see a subset of the volume that the production test saw? Probably so. Yeah, I mean, it would seem the reason, if nothing else changed in the system, that the production test saw more than, but the same as, the shut-in test. Therefore, if you were trying to see how the system looked as it aged for the longest periods of time, the build-up test and the shut-in and the production test, I'll cross my fingers when I say this, because I don't believe it's quite true. Well, it's not true. Presumably, the shut-in test and the production test gave you the same results. Same KH of the system, same XF, same P star, all that stuff, okay? But the difference was that the build-up test only saw this much, and the production test saw that much. Well, I would argue to you that there are two pieces to that puzzle. One is, I would always rather see more than less. Okay? The second piece of the puzzle is, if I'm going to see less, then wouldn't I be wiser to conduct my analysis in a setting where I'm making money rather than spending it? Darn right. Okay, I just found a reason why I don't want to do a build-up. Because I can do the production test. If I use the same degree of diligence in the production test as I would for my shut-in, I'm going to get the same data. And I'm going to get it while I'm making money rather than spending it. Now, have I just said something horribly bad about doing well analysis? It is not my intent to do so. Because I know and you know we will continue to do build-up tests.
Well, and really where this question came from is on a brand new well. I've been looking at some of the stuff on the Mancus wells up in the Farmington San Juan Basin, that's where I'm from.
Yeah.
And, I mean, they've got, one well's got 10 months of data, is all that's up so far. And so, but they do have a few build-up tests.
Yeah.
And so, I mean, when you're looking at a well that's only a year old, can you still do production?
Absolutely.
You still have
Because
production?
the same math applies to the build-up as does to the drawdown.
Okay.
It's the same math. So you are simply, well, again, it goes back. One of my clients, I got into quite a squabble with them. They had had a series, they produced a well for a week, shut it in for 12 hours, put it back on for 36, shut in for 12, 36 on, shut in for 12. And we got into this big argument about, well, the data that is a result of those 3 shut-ins is far better than the whole data set. Well, the bad news was the shut-ins, because there was some liquids issues, because there were some major stress issues in this system, portrayed a very poor picture of the system behavior. The production history showed a very different characteristic to the system. And my thesis is that production data is more useful because it shows you the condition of the system when it's making money, not when it's sitting there costing you something. It's that simple. I mean, the bottom line is, my goal is make money. Make money. Make money. Oh, by the way, make money. And if I can conduct a test in such a way that I get the same knowledge and make money, it's a far better strategy, regardless of what the results are. Because what I would like to know, the thing that I need to do as an engineer is find out what is the, well, it's kind of a gross, crass kind of picture, but I think it's appropriate. You go to the doctor for an annual physical, okay? He goes to the doctor, and he says, Doc, I need to know how well I am. Would you rather know how well you are when you're alive and your heart's beating? Because the doc says, well, I have a choice. I can shut you in, dead. He says, well, we refer to a shut-in. The well's dead. Well, think about what that implies. You're going to go to the doctor for a physical, and he says, well, I got to shut you in. You're going to die. That's a pretty crappy way to do business. But that's what we do. We call that a shut-in. We call it a build-up. The medical analogy is, I'm going to go to the doctor, and the doctor's going to say, well, I can really find out how healthy you are, but I got to kill you. And then I hope I can revive you. Yeah? Well, there's a really important piece of news. In that same shut-in study that I did, on average, 1 in 7 of the wells were enhanced by the shut-in. 1 in 5 of the wells were killed, dead, no further production. Whoa, that's not okay. And the reason I tell you that crass analogy to the medical profession, if I'm going to do a shut-in and I run the risk of killing the well such that it will not produce again, should I do that? I just spent $15 million buying this thing, drilling it, completing it, buying pipe, running the frac jobs, what have you, and there is a risk that if I shut it in, it will no longer produce. Ooh, that's not okay. Don't go there, Fred. But this data set that I have is a population of actually about 500 wells. 1 in 5 of those wells, when shut in, did not produce again. Oops. That's pretty scary. Yeah, it really does. So, I'm sorry.
So under what conditions does shutting enhance production?
I honestly don't know. The question was, what conditions exist that a well will be enhanced by shutting? I really don't know for sure. I did some numerical simulation, and I wrote a paper in 136, 523 or something. Doesn't matter, because it's a piece of junk. The analysis showed, the simulation showed, in wells that had a gas saturation in the fractures were less harmed, less likely to be harmed by shutting. This is classic, it's just numerical simulation, so you know, I mean, it's like, okay, pick a setting that makes the dryer come on. And that's kind of what I was doing, was what kind of conditions can I create that will allow the well to be enhanced? Because what would happen if the fractures had a gas saturation in them at the start of the shut-in, then they had a volume of accommodation that would pressurize as the well continued to be shut in. And when it was put back on production, those gas bubbles would expand and expel the fluid back out of the fractures. That was the only scenario that I was able to come up with that created a situation where the well was equal to or better than pre-fracture or pre-shut-in. Now, I mean, you start thinking about it and you say, wait, you know, that's one out of a zillion possibilities, and I can see that. And that's why it's kind of a junk piece of work. You know, nowhere close to considers all the possibilities. Okay?